to introduce my colleague and dear friend, Scott Prahl. Scott is currently a professor at the Oregon Institute of Technology, where he leads the optical engineering program there. But as way of background, he finished his undergraduate degree at Caltech with a degree in applied physics, and then went to UT Austin to do his doctoral work in biomedical engineering, where he worked with A.J. Welch, who's one of the pioneers in the field of biomedical optics. He did many things, I think, during his PhD, but I think the work he's most well known for is his work in light transport in tissue, where he did a lot of the pioneering work in establishing the first Monte Carlo models for radiative transport, and also developing kind of rigorous diffusion approximations to solve or approximate the radiative transport equation, and establishing the use of integrating spheres for ex vivo measurement of optical properties. After that, he went to the Wellman Labs of photomedicine to do postdoc with Roxy Anderson and others. And that's actually when I met him for the first time in the early 90s. When I was a PhD student there, he was a postdoc at that time. And so that's when we first met and had many enjoyable times in the lab and at lunch. And then he moved on to, actually, that was after a short postdoc in Amsterdam, right? Yeah, so immediately after his PhD, went to Amsterdam and did work with Willem Starr and Martin Van Hemert and others there. And then you moved on to the Oregon Medical Laser Center, worked not only in diagnostics, but also in some therapeutic applications, use of lasers to break up clots in blood vessels, amongst other applications. But throughout his career, he's really worked on the interface of instrumentation, both for diagnostics and therapy, fiber probes for diagnostics. So he will talk about a topic that's near and dear to his heart, and you'll see the radiative transport equation by popular demand. They want to see a rigorous derivation. So
sure.
Okay, let's welcome.
Thank you, Vasan. Vasan had no gray hair when I knew him. He's somewhat older at the moment. So before we start, how many of you know slightly more than nothing about Monte Carlo?
Yeah.
It's up to you. You can say, well, I can say the words. I know. How many of you have actually used Monte Carlo programs to solve a problem? So just a few, 3, 4, 5, yeah. How many of you written a Monte Carlo program? I'm sorry. just a handful. And then how many of you have asked AI to write your Monte Carlo program for you? Because I did that last night, and in 1 minute and 40 seconds, it did what took me 6 months or a year to do, because I was flailing in the dark, and trig turns out to be hard in spherical coordinates, because you have a photon going this way and it goes this way, and you go, where is a new photon? And it turns out that there are very simple ways of doing that once you know the trick. But until you know the trick, you go, oh well, I need to rotate. And then my physics background was like, oh, it's all spherical rotations, rotation matrices. Anyway, I did this last night. I wrote a program, and it worked like it's terrible. This is supposed to be light coming down from the top. It's supposed to have a radial profile. Nothing is quite right about it. So, which brings me to my next point. Why should you listen to me about Monte Carlo? First of all, you're polite, and I thank you for your attention. I wrote a silly Monte Carlo program for my PhD because at the time nobody had done it, so I said, let's do it. I have complete confidence in Monte Carlo, and I have no confidence in a Monte Carlo simulation. So you can work both ways. You can be completely confident that your whatever Monte Carlo model is good and accurate and is simulating exactly the problem you want. The trouble is that modeling is an imperfect representation of the real world, right? You make all these assumptions and you say, oh, the boundaries are perfectly flat so that you can use Fresnel reflection, but you know that your skin is bumpy and that it goes up and down and that the reflection from the skin is going to be weird, at least unless you put a index matching fluid on and then a piece of glass, for example, to make it so that the interface is a nice plane boundary. So why use Monte Carlo? In principle, there are no problems or no restrictions on the geometry. So almost always, any interesting problem is going to have weird geometries. You're going to be taking your you got light coming in one place and you're looking for some sort of effect somewhere else. And then there's bone in between, or there's vessels, or there's something that you're interested in figuring out what's going on. And so Monte Carlo allows you to include the features that you think are essential in your problem. And you can then ignore the rest. And then the other thing is that you can figure out how accurate your Monte Carlo program is just by rerunning it. You rerun it and you do it 5 times and just take the average and standard deviation of the results, and that gives you an estimate of how bad your thing is. This is assuming that your Monte Carlo program is written properly and that you don't have systematic errors. This is just straight up random errors. It's intuitively appealing because you say, Monte Carlo, I'm just blindly, I'm tracing all these photon paths, and it's simple. There's absorption events, there's scattering events, there's reflection events, refraction events. You just track these. And if you have an absorption event, then you can say, oh, well, this is going to go all into heating, or it's going to go into fluorescence, or it's going to go into Raman scattering or something. So Monte Carlo is super old, 1947. It was just after the war, and they were interested in neutron collisions to determine what criticality was. So von Neumann said, oh, well, let's do Monte Carlo to track neutron paths through whatever the stuff that we're doing. The Monte Carlo name came from another project leader, Nick Metropolis, who's knew Ulam, who's a famous mathematician, whose uncle would borrow money from him so he could pay off his debts in Monte Carlo. So that's the only reason that Monte Carlo gets the name Monte Carlo, other than we got the rolling of the dice stuff. But it actually goes back to gambling debts. Some things stay the same. And this, I doubt that the processing of 100 neutrons will take much longer than the reading, punching, and what sorting time of 100 cards. That is about 3 minutes. And still, with Monte Carlo, if it takes longer than 3 minutes, I lose interest, and I stop, and I go, I got to do something else, because 3 minutes is as long as I'm willing to wait for an answer. So you know about VTS, and it's kind of the synthesis of 3 different things. There's the photon biographies, this whole idea of numerical integration and then combining that with the radiative transport equation. And the idea is that VTS will supercharge your Monte Carlo program. So first of all, we'll talk about tracking photons. Before we start, I got to say a bit of history. Way back in, I don't know, this must be 85 that we did this work, that we had a Heaney laser. We had this made up fish tank. It was about this big, and it had black sides, and it was filled with water, and we put our samples right in the middle. We put a sample there with sections of skin. And then we had a motor on this, and then we had an optical fiber that would go around in a circle and measure how much light was coming out from each direction. Because we wanted to know about scattering. You know, my whole thing for my PhD was, oh, everybody is just assuming isotropic scattering. That can't be right. And so it turns out it was not right. On the other hand, it also turns out that it doesn't really matter. So, so I got that going for me. Anyway, this goes around in a circle and measures the amount of light in each direction. And so if the light hits here and goes more in one direction, then you'll see a peak there. And then we recorded this, and you can see that we had a real CRT for our this monitor for our computer. So here's our sample, and the laser beam would come in, hit the sample, some would come backwards, most of it would go forwards. And what we were interested in is what happens with single scattering, not what happens with multiple scattering. So if you have a thick sample, you're going to get many scattering events, and the actual individual scattering event is lost. So what we did is we kept sectioning, and we get smaller and smaller until we got to, I think this is a 20 micron section. And you see that this 20 micron section is quite forward directed and somewhat fortuitously, the original Monte Carlo, or that measurement was done at Wellman by Steve Jacques, and he had his data and he was fitting it with Gaussians, and none of the Gaussians were working. And finally I said, well, have you tried the Henny-Greenstein phase function? Because I had just been reading the astronomy literature, and it turns out the Henny-Greenstein phase function worked great. And so it fit nicely, and we would find that the anisotropy was about 0.9. So if you look at the history of the Henny-Greenstein phase function, it turns out they just made it up. They said, oh, this is a nice formula. I can change the anisotropy from -1 to 1. The shape of this goes down to a circle, and then it goes back the other way when you have backscattering. So it was very simple, mathematically tractable, had no physical basis at all. It was just they had no idea what the scattering was for, these stars or whatever they were looking at. And they needed to come up with something. And so that's what they did. They just came up with function that was mathematically tractable, and then they could do their calculations. And it turns out it's sufficiently mathematically tractable that you can generate direction cosines based on whatever your value of the anisotropy is, G. So if you have an isotropic distribution, this is cosine theta. So you should have values between 0 and 1 for your direction. And it's easy to come up with uniform distribution. It's harder to come up with these weird distributions, and there's a whole class of random variable stuff that allows you to come up with a closed form way to generate these values. So these are bins with, I don't know what I did, 100,000 values, and then I just figured out what the bin size was for each one, counted them, and showed that the overall result is that it follows a distribution where it's mostly forward scattered and it's weakly backscattered. So we're going to use Henny-Greenstein scattering in the Monte Carlo. And we're going to start with the stupidest, dumbest Monte Carlo program you can think of, which is the one that I thought of first. And the idea is you have your photon come in and you move a little distance dx, small distance. And at this point you say, was I scattered? Was I absorbed? And if you got no to both of those, you continue. And you continue until you get to a place where, oh, this time when I roll the dice, I'm scattered. So you generate a new direction based upon the Henny-Greenstein phase function, and you go in that direction. So you change directions, you start traveling that way. You keep going these small distances, and you get to another place, you scatter again, and then eventually you roll the dice and you're absorbed. So you save this one point. So we've done all this calculation for at each of these points, and it's super slow. So, you start the photon, you move it a little bit. Is it still in the medium? You keep going, you say scattered, then you change the direction. If it's not, then you absorb, then you start a new photon. And it's very easy. It's super inefficient. So we're going to improve the program by saying, okay, let's move the photon to the next scattering or absorption event. This is, the idea is that before we were moving just a small step each time, and we were saying, did it happen, did it not happen? Turns out that we know the distance to the next scattering absorption event because that's given by Beer's law, just e to the minus the distance. And when we invert that process, we find that if we take the log of the distance and divide it by the total scattering coefficient, then we get a random number that tells us the distance to the next place where an absorption or scattering event definitely happened. We don't have to do all those intermediate calculations. So now the light comes in, hits, gets refracted, goes to, we move to here. We know that the light was scattered or absorbed at that point. We can say, okay, it was scattered. We're going to move again, move, and then we move one last time and we're absorbed. Each time, the chance of an absorption event happening is just the ratio of the absorption to the absorption and scattering. So it's the fraction, it's just a fraction. This will be from 0 to 1. If mu sub s is 0, then your 100% chance of absorption if mu sub a is 0, then there's no chance. So as you're sitting there waiting the 3 minutes for the Monte Carlo program to run, you keep saying there's got to be a better way. We have to be able to come up with some more efficient way. And the next thing you can do is you can say, oh, well, there's no reason that I'm sending one photon at a time. I could send 1,000,000 photons along that same path. And that means that Now, at each scattering and absorption event, some fraction of light is always absorbed, and you just keep going at each time, and you have more absorption at the beginning. You have fewer photons that make it to this point, then some light is absorbed here, and then more is absorbed. And so you keep doing that, and so you're able to, once again, the fraction absorbed is just given by this. So we've gone from doing all these intermediate calculations to just immediately going to one, the first scattering absorption event, we always absorb there, and then the next one, and everything becomes we get a little bit of data every single calculation, which is what you want when you're doing, 1 million of these or 10 million of them. So the next idea is to say, well, actually, let's pretend that absorption isn't happening, because absorption doesn't change the path here. And we're going to say, we're just going to deposit light all along this according to Beer's law, because we know how many photons are there, we know what the absorption is, and then we're able to figure out what the absorption along that line is. And so that's the idea, is that along each of these, we absorb at each point. So we have a background grid where we're tracking all the absorption, but we are able to figure out what the absorption is. So now we don't get just data at these 3 points. We get data at every point along here, and every point along here, and every point along here. So all these things go together to make everything so that you can wait 3 minutes, but you get less noisy data, or less noisy.
So Scott, let's pause there, since you're going to kind of shift topic, and just want to see if there are any questions
I dare
from
you.
the audience. Let me get you the microphone.
I'll just repeat his question.
Can you go back to like 3 slides back? Yeah, I mean, forward. Yeah, forward.
Forward.
Yeah, that's good. I'm just wondering, like, how do you decide the distance that the photon will be absorbed or scattered, this distance? I think that's something maybe missing in my knowledge. Yeah.
I should have spent more time on this. I should have created one more slide. I'm sorry. So the idea is that Beer's law, e to the minus mu sub a plus mu sub s times d, describes how far a photon travels on average before. So you have an exponential distribution in the tissue for single scattering. We're only talking about single scattering and stuff. So this is the distance for an absorption or scattering event is always this exponential. And 1 gives you, if e to the minus 1 gives you the average value for that. You throw in the mu sub t, that's why we divide by mu sub t, so that we convert from this arbitrary, or this normalized version, to a scale that's appropriate for your problem. So in our simulation, most of the photons travel a long ways. And fewer travel a long ways, 4 mean free paths, because they just can't, they undergo a scattering or absorption event before they get there. So we know that the distances traveled follow this distribution. And we can generate distances by taking the log of a random number between 0 and 1 and dividing by mu sub t. And that will give us, we can, when we generate the values, here I've generated the values and bin them, and you see that it follows this exponential. So the trick is to remember that we're talking about single scattering, single absorption events, and that tells us what the distance is to the next scattering or absorption event. Did that help at all?
Yeah, because it's actually it's a number like a variable.
Yes, the random number is this number, and you put it in this, and you can get any one of these values, right? When you take the log of the random number, and most of the values will be here, and few of them will be out here.
Another way just to look at this is that this is the actual random number that you're going to generate from your random number generator.
That's
and
the
then,
number of random numbers of that value.
right, and then you just read off. If I
Yes,
happen to
yes,
do 0.6,
yes.
okay, I better step this amount. But if I get a 0.2, I will go that distance. And then over time, after you generate so many random numbers, you basically recapitulate this exponential
Yeah.
distribution.
And you say you, for example, inject 100 photon, do they share the same random number or they have 100 random numbers?
So depending upon which model you're using, you can do it with just one, or you can do it with 1,000,000. And it usually is like 10,000 or something.
Okay, so in this case, each photon has a random number.
Yes. Each step.
Each
So here we generate a new random number each time at each of these steps, and we say, was it absorbed or scattered? If we're moving all the way to here, then we generate another random number to say, is it absorbed or is it scattered? And based upon that, then we change what we do.
Okay, but I think that the clear story basically tells you the distance of each step.
So yes, you're right. If we're generating these random numbers as the distance, but that's the whole point, is we're generating random numbers to decide our entire life. Are we going to go to the store? No, I rolled a 3. So here you generate the distance to the next step, and then you roll new random numbers, and you don't use this. You just are like, is it bigger or less than the fraction of scattering to absorption?
So I think maybe it may clarify, you actually have to, depending on the sophistication and which method of Monte Carlo you're using, intrinsically you have up to 3 random numbers that you need to generate. One is to figure out the step size. One is to figure out at the interaction point whether you're absorbed or scattered. And then if you are scattered, you then have to generate another random number to figure out what is the new direction that the photon should propagate after that interaction. Right.
What is this random?
So this random number tells you what step size you should take between the individual interactions. There's a different random number or different distribution.
So here, this Cassie is a random number between 0 and 1. You plug it in here, and this will give you your new scattering direction.
You can also generate a random number to figure out whether you're absorbed or scattered at that interaction. Yeah. Okay. I think we have another question. Yes.
I just have a comment related to Michael's question. Again, in the 2 plots for the different histograms, can you go to that slide, please?
Which slide?
The same as before. That one. Yeah.
Okay.
So it's basically you have the 2 horizontal axes with some value, So as I understand, the horizontal axis on the left is the value for the random number, right?
Yes, so this is showing that our random numbers vary between 0 and 1,
Exactly, yeah.
and that they're all,
It has a uniform distribution.
they have a uniform distribution.
Yeah.
When you plug them into, when you just take minus the log of the random number, then you get this this distribution of
Yeah, so the horizontal axis in that right plot
is in mean free paths.
minus log C divided by mu t, right?
No, there's no mu sub t in it because this is dimensionless.
Oh, dimensions. Okay, yeah.
If I had thrown it,
Yeah.
I could say it's, so
Okay.
this is just mean free
Yeah.
paths.
Yeah, that's.
Does that make sense now?
Yeah. Thank you.
Any other questions?
I'm sure it's all clear. You get an A for sucking up. Yeah, so we did this, and this is the last piece is what happens as you go from one boundary to another. And we can use the same formalism because we can say when we're going from this point to up here, that we generate the same random distance based upon minus the log of the random number, and that'll tell us how far it goes. But that assumes that it's all the same, but we know it's not the same. In fact, we know that the distance, there'll be a different value for the total scattering absorption in one medium versus the other. And so, but overall, we know that the sum of those two has to be this distance, the mean free path that the photon has traveled. So in principle, you can just do simple geometry to figure out what this distance d2 is, which will, and since you know what mu sub t in part 2 is and mu sub t in part 1 is, you can figure out what d1 is. And then you can figure out your distance to the how far it goes here, and then it's going to go a different distance in the other medium. Because it has different optical properties, it could be clear, it could be more cloudy, it could have higher absorption, whatever. But you say, what if the indices of refraction are different between the two boundaries? You know, that's totally likely that it's going to change. And so that means you just have to throw in Fresnel refraction at that, or Snell refraction, just simple Snell's law, and then you do the same calculation again. And of course, at this interface, if the two are different, then you have a chance that it's reflected from that boundary. So what do? We generate a bunch of data for the absorption. So here we have W, the weights. So this is assuming you start with, I don't know, 10,000 photons. And then at each step, you have some fraction of those that are deposited at X, Y, Z1, theta 1, phi 1 for the direction that the photon is traveling at that point. And we save the weights, and we save all of these weights. So we can generate a giant file with all the photon histories. And if we just look at where the absorption events happen, so we have our grid, and we take a section through, and we can look at how much light is absorbed in each point. And this gives you a starting point for later calculations. Yeah.
Question regarding the boundary, when you hit the concrete and you track reflection. So now the photon split into almost like two different tracks. You can track both.
Yes, you can. So the question is, at the boundary, you got photons going up and you got photons coming down. And then suddenly you go, oh, am I going to make my Monte Carlo program recursive so that I can do follow one path all the way to the end and then I follow the other path? And that's too complicated for me. I just roll the dice. I say, you're either going to be reflected or you're going to be transmitted. And then I can keep it more simple. There's fewer things that can go wrong.
Thank you.
But you can totally do the other and track both and keep recursively calling your. I have no idea why I put this in. So diffusion theory is an approximation of the radiative transport equation. You simplify it down so that there's only two terms, and that can give you a reasonable approximation. But what you see in this thing is that the solid line is the Monte Carlo result. And the diffusion works quite well at long distances. So as you get farther away, but it works very poorly right here at the pointy part of, this will be the place that's hottest or is generating the most signal or doing whatever. And so this is kind of why just simple diffusion theory will only get you so far. And it's part of the reason why I wrote the original Monte Carlo program that I did was because, well, a whole variety of things, but I was generating negative reflectances with the diffusion equation. So,
and it's even worse, right, than it actually looks. This is on a log scale on the y-axis. So even
oh yeah, yeah.
at
So
like
this
5 or
is
6 millimeters.
yeah,
it's
this
really
is
bad.
like an order of magnitude nearly off.
And so even up
and
to like
it's
R of 5, you're probably off by 30, 40, 50%.
Mm-hmm.
Yeah.
But if you don't have good data, good experimental data, it's good enough, right? It's like no one's going to argue with you because. So how can we improve this Monte Carlo's thing? And the idea is that we have a way of tracking photons and keeping all their photon histories. But we'd like to put in some more knowledge about the whole process. We know that the radiative transport equation has to be satisfied. So can we use that to improve our statistics? But before we can do that, I have to talk about numerical integration. How many of you have taken a numerical integration class or what is numerical methods? So what are the ways you integrate numerically? Numerical, yeah. You did Monte Carlo numerical integration? That's excellent. You don't get an answer. Anybody else? Shapes, what kind of shapes? Rectangles, that's the classic way of doing, if we're going to integrate f of x from a to b, we generate values of f of x. And, we see how many we have in each bin. So we've generated all these values and we just plug in random values and you have your rectangles And you just add up the heights of all the rectangles. Classic calculus. Calculus 1, 2, 1.5, whatever it is. Incidentally, I had to substitute for another faculty member, and I taught calculus 1, and I was appalled by what they teach. I was like, this stuff is ridiculous. Nobody uses this. I have not seen this in 35 years. And the students were unimpressed. So, you know, the first time you do this, you say, well, all those rectangles here are kind of, oh, wait. Why are you going? There we go. So we would like to use these, connect the points so that we have trapezoids. And if we do that, then we get a slightly better approximation to the integral that we have. And this is an approximation with 1, 2, 3, 4, 5, 10 rectangles. So it's better. Here it was 944. There's, oh, it's the same. Oh, that's right, because when you do the rectangles and you add them together, then they all average out. Yeah, I'd forgotten about that. But this Gauss dude, I don't know if you've heard of him. He's super smart. And he said, I don't have to make my rectangles uniformly distributed. I don't have to make them the uniform width. I can change the width so that when I come up with these points, each point has a value and it has a width. So you have weights. Basically, you have a set of abscisses and weights. And what this allows you to do is that if you have 10 points, this means that you can exactly approximate a polynomial of order 19. That these 10 points, you generate them, and you will get the exact answer to, and you go, and Gauss quadrature is used all the time because of this. But of course, we're not Gauss. Instead, we got this Monte Carlo stick that we're going to wave at everything. And what we're saying is, okay, let's just randomly generate our points. So we're going to have 10 random abscisses. We'll have widths associated with each one. And we can figure out what the overall integral is. And it kind of does not work so well. So why are we going to do this? We could say, oh, we're just going to use a lot of points, but then you go, well, I could have used Gaussian quadrature and only had to do 10 points instead of 100 points. And this is what it takes to get to not even close to what the Gaussian was. So Monte Carlo is not useful in one dimension. It starts being useful when we're doing double integrals or triple integrals. Because if we're going to do this double integral, we have to do this inner integral first, and that can take 10 points. And then we have to change y, and then we do the integral again, and then we get another point. So we keep doing it, and because you have this n squared problem, it becomes very, very slow. So here, a simple, just to figure out what g of y is, we'd have to do endpoints. But for every value there, we have to do endpoints. So ultimately, we end up with n squared values. So if you're doing traditional quadrature, in 1D you'll have n, in 3D you'll have n cubed, in 5 dimensions you'll have n to the 5th. So, and if we have 6 variables, then it becomes very, very big. And what the advantage is that we can do these random Monte Carlo integrations with fewer points. Well, let's just talk about this. So in this case, we do, going back to the Monte Carlo integration of a single integral. We did it. We come up with 10 points. The integral value is the average value of the function. We go from here to here. We find it's the average value of the function. That's the sum over n times the range that we are integrating over. And we know that the variance of our function or our whatever value will decrease as 1 over n. So this is standard random variable. And so in 3 dimensions, we have these 3 integrals. We're generating an average value of our function. We multiply by the dimensions in each direction. And then we divide, well, we've already divided by n. But our error here for f is going to go as 1 over n. And so that means that Monte Carlo works super well for multidimensional integrals. And in fact, you know, like Mathematica has built in Monte Carlo solutions for numerical integration and it becomes very useful for high dimension integrals. How many know that radiance is power over area over solid angle? You know why this is?
Raise your hands, right? Come on.
This is cool because it's conserved. The radiance does not change as it propagates through space, through medium, it stays the same. And so it's kind of why microscopes, you cannot, you know, the solid angle gives you the angle that the light is coming in at. So in a high power objective on a microscope, it's going to be a very wide angle, and at a low power, it's going to be a narrow angle. And so that changes this value. But that also means that the area that you get to image is quite different to get the same amount of light. And so but that has nothing to do with this talk. The radiance is the power over the area over the solid angle. And that's what will denote the radiance by L. And we see that in a time-independent one, the radiance at any point in this room depends on X, Y, and Z, as well as the direction you're looking. So if I took a radiometer and I moved it, and from this point, I pointed at the light, I would get a different value than if I pointed at you, because you are not as bright as the light. So it's 5 values that the radiance has. And then we have our radiative transport equation. And this says, what is the change in the radiance in the direction omega? This is just a vector, unit vector. And that change in radiance is going to be whatever was gained from all other directions at that point, we're going to have some loss due to scattering or absorption, and then we'll have some contribution from a source. So at any point, we can figure out what the change in the radiance is in a particular direction related to the gain from other directions and the losses. What you notice here is that we have a differential on this side and we have an integral on this side. And you say, I only know how to integrate because I just learned how to Monte Carlo integrate. So I have this hammer, I want to use it. So you go back to your differential equations class and you say, well, if I have a derivative let's just do one dimension, and it's we have a derivative, we have another term that's the scale times the radiance, and then we have a source term. And we define an integrating factor as the integral of the absorption versus its position in space. And formally, we can say our radiance is equal to this integral of a mess. What this means is that we can take this equation, which is exactly the same as what we had, this equation, and we put this in, and then we just substitute in for all these other things, and you get two equations. So you're going to get this integral, and inside we're going to have this other integral as well. And so what it ends up looking like is we have a kernel function times our radiance integrated over all positions and directions. And our kernel function is defined in terms of a collision integral and a transport integral. So this tells us the probability of a collision or a scattering event. And this tells us how much light gets from one point to another. And then our source term is simple. Here's our actual source, and the amount that gets to any position depends on the direct transport from the source. The transport factor depends on the total scattering and absorption coefficient at every point, and that's going to vary along this line as our medium changes. So, so we have our transport factor, we have our collision factor, which is just directly related to our scattering function. And we put it in and we solve, and formally we get this kernel times this. Once again, what we see is we have this average value from the Monte Carlo, which means that we could do a sum directly, except the kernel is a mess. So we have to integrate the kernel as well. And so you have a double integral, and this is all post-processing. And fortunately for you, this is all buried in the VTS software, so you never have to see it. You don't have to do these things. This is just motivating you to say, VTS does not suck. Post-processing, I'm sure Carol's going to talk about this, but you got light coming in here, you've created some sort of field, but you only are interested in this one point. And so calculating what happens at that one point, if we had to only have photons that come to this point, it would take forever. And so by leveraging these radiated transport equation techniques, we can simplify. So you can do integrals, with the radiance and then the area for this. This has, we have light coming in here and we want to know how much comes out someplace else. These are trivial examples. So to close, Monte Carlo is at least 75 years old. Everybody hates variance. Everybody hates the bouncing around. And so that's why all these mathematical techniques have been added to make it converge more quickly and have less variation. You can get huge speedups in the processing. So if you want 10 to the 7th speed up, you have to, it's possible for certain class of problems. And there are nice implementations available. So you do not have to rely on AI to write your own Monte Carlo code. So the VTS was led by Jerome, and it was done in 1962. My brand new work on Monte Carlo was done 25 years later because I did not have access to this because the internet did not exist. Jerome wrote this nice book about Monte Carlo principles. It's completely opaque. Nevertheless, our next speaker, Carol, her advisor was Jerome, or Jerry. So you're learning from the best, or second best anyway. So, any questions?
Mr. Scott. All your questions about the RTE can come now.
Yeah. It's a slog, yeah.
So you said the Monte Carlo method was like invented like 75 years ago or something like that, and it was
75 years ago, yeah.
Yeah, and it was applied for neutron transport problems, right? Do you have track of when was the very first implementation for light propagation in optically turbid media?
Brian Wilson.
Yeah, I think Brian Wilson's paper was an early thing. He did not do anisotropic scattering. That's what I added. But Wilson was in 86, 87.
Okay.
So that's the first published for tissue stuff.
Yeah.
Yeah, all the the equations are identical between this. The only difference is you don't have to worry about the neutron hitting and then changing speed because the photons all are the same speed. They scatter and so you don't have to worry about other things, but it's actually a simpler problem. Yeah.
Sorry, I should know the answers to these, but I don't.
Just think of me as an AI where there is no shame.
A much more accurate AI than ChatGPT.
Well, not necessarily.
So my question is, you mentioned the problem with having complicated geometry in tissues. And at least from my understanding with the VTS software, we usually voxelize things. How do we deal with something that's curvy, such as like a sphere, when you deal with the boundary conditions, when everything is voxelized? And how can you calculate the angle at which the photon would interact with the surface or something like that?
So you're thinking that, for example, you have a spherical probe that's glass that you're putting into a tissue and you want to know how that's going to interact. And that's in a completely random tissue that has varying optical properties everywhere. Don't do that. Yeah. I think I would triangulate. I would assume more uniform stuff, and then because then you could do the sphere directly in the simulation, and then compare that to discretized sphere. You could also, I guess, you could. The reduction of shapes into triangular meshes is super good now. There are nice algorithms that did not used to exist. And so does VTS require a rectangular grid?
We have certain geometric shapes. So we can do spheres, cylinders, ellipses, ellipsoids, anything that has an analytic equation that describes its perimeter. We have those kinds of options. We do not have tetrahedron mesh available. Yeah.
Yeah, that would
Yeah,
have
so
been the next
there-
thing I went to, is a tetrahedral sort of.
I mean, there are kind of two broad classes, I think, of Monte Carlos. One is the VTS, where we kind of describe all shapes using conic sections. So there's an analytic solution for a ray intersecting any boundary. And then, of course, there are all of these methods that are voxelized, use different ways of subdividing. And I think there's an old paper by Amir Ganjbach's group that talks about, you know, if you have an undulating surface and you triangulated, what are the errors incurred because you're making approximations for the local angle of intersection between. And so, but I think now, you know, the voxelization has improved quite a bit, and computational power is sufficient that you can subdivide to sufficient accuracy.
Yeah, it turns out that's a really important problem for these atmospheric models, is that wave motion on the ocean, you know, there's a good fraction of the Earth that's waves. And so you cannot just say it's a flat boundary. If there's turbulence, then you're going to have very different interaction of light with the water than otherwise. So, and that's been an ongoing set of arguments in the climate model world for forever.
Other questions? Okay, so let's close. Let's thank our speaker once more. Got a bit of a break until
Was I supposed to keep talking for another half hour?
that's okay.
No, no.
You don't have to.